focus for this week is the path analysis approach. I have to share with you a little bit about my experience with path analysis. It was one of the 3 statistics courses that I was recommended to take by my advisor at Ohio State. He recommended that I take it in the sociology department, and not knowing any better, I followed up his recommendation. I found out that it was the worst class that I had while at Ohio State. The professor was the most profane. There were sociology PhD students in the class who were taking it for the 2nd and 3rd time. Not only was the professor profane, but he was not a very good professor. And so I spent a whole semester on path analysis and took my C+ and was happy to escape the class. So I bring a lot of baggage to the discussion of path analysis. I must say that my study and preparing for this lecture and assisting you has given me a better understanding and a better appreciation for path analysis, and it didn't have to be as complicated as that professor made it. So I'm hoping that through my explanation from my past experience with difficulties with path analysis, that I will make it a little bit more workable for you. I believe that our textbook does a great job as well, and I'm going to try to break down some of the ideas in the textbook so that you can see the trees in the forest so that you have a better understanding. Where are we at this point? Well, we have been talking about relationships. And when we look at relationships, we've been talking about the idea of correlation when we were just looking at the relationship between 2 ideas. Regression when we were using the idea of correlation to do predictions, and then multiple regression when we had several independent variables that we were predicting on a criterion variable. All of these were still looking at the idea of relationship. But now we've crossed the bridge of the river of effect, and we are moving to the place where we're using correlations or regressions as an idea for causation, and that's what path analysis is doing for us. It's using the idea of the regression or the idea of prediction that we've been moving closer and closer to, moving from predicting a relationship to now saying that we have a cause and effect that's coming as a result of this theoretical model that we've created. As we move into the idea of path analysis, we need to understand the idea of causal modeling. Now, causal modeling is a model, a theoretical model that the researcher creates based on a literature support. So as you've read literature, as you've looked at theories, you begin to say, here's what we're proposing to be the ideas, the variables that are causing this variable that we're looking at to change. Now, there are 2 types of causal modeling. First of all, there's path analysis, which is the focus of our discussion, and structural equation modeling, which, as your book explains, needs higher level statistics program and really beyond the focus of our course. So we're going to be focusing on path analysis as we work through our course. Within that idea of path analysis, we need to understand 2 caveats. First of all, the inferences drawn are much weaker than if the results were from a controlled experiment. We build a theoretical model based on literature and theories that have already been proposed. And from that, we're saying we believe that these are the variables that are impacting the variable that we're looking at. If we could set up an experiment where we could test how one variable causes a change in another variable, our results would be much stronger and our inferences would have a much more strength to them. But path analysis is a good place to start in theoretical building to give us an idea of where to do some experiments. The second caveat is the results are valid and unbiased if the theorized model reflects what is really causing the change. And that's why we do both the literature development for the model, and then as we're going to see in path analysis, we're going to test that model to see if we can find the best fit for predicting the change and what variables are causing the change that we're looking at. To me, one of the most important aspects of path analysis is that we understand the nomenclature. And once we sort of understand what's being shown, then path analysis is not so daunting. And so I want us to take a few minutes and look at some of the terms that are being used as we move through the idea of path analysis. First of all, there are two types of variables. The first one is the exogenous variable. And those are the variables that are in the model that explain the change in the variable being examined. These are the ones that either have a direct effect on a variable or an indirect effect. And this is sort of going to be where you have to look through that, because an exogenous variable may change from an exogenous variable to an endogenous variable, which is a variable that is being explained through the causation of the other variables. So if you have a path that has three variables in it, say we have Z1, Z2, and Z3, then Z1 is going to be the exogenous variable on Z2, and Z2 will be the endogenous variable that is being impacted by Z1. However, Z2 is the exogenous variable on Z3 because it is the variable that is having a direct impact on Z3. So you're going to have to make sure you understand when a variable is an exogenous variable and when a variable is an endogenous variable. Path nomenclature is also something that you want to make sure you understand as you look at the models that are presented. We have a P, and that is a path of causation. If it's an R, then that's a path of correlation between two P variables. So the P variables usually are going to be those that are going to be exogenous, and they will have a correlation between those, and their path will be represented by an R path. And then we have the Z, which is the variable whose change is being investigated, or it can be the other variables as well, because we're looking in relationship to the Z-scores of those individual variables. Now, how do we understand the numbering of the path indicators, or the P paths? The first number that is in the subscript is the variable that's being explained, and that is the endogenous variable. So under the P, the first number, the subscript, will be the endogenous variable that is being impacted by this variable. Sometimes with these P's, a variable can be both an exogenous variable and an endogenous variable. It's according to where it occurs in the path. The second number with the P is the variable theorized to have a cause and effect on the exogenous, and these are the exogenous variables. So you see that each P number will have an endogenous variable number and an exogenous variable number. And this is depicted by a straight line with an arrow on the end of the line toward the endogenous variable. So here's our example. We have P with subscript 4,1, and that we have direct causation on variable 4 by variable 1. And that's how you would read that subscript. The numbering of the correlation indicators is very similar, and here we represent this by R. And the first number reflects the correlation between two exogenous variables. And the first number is the smaller of the two. So if you've got variables 1 and 2, the first number is going to be 1. But if you had variables 3 and 4, the first number would be 3. And the second number is the other number. So in our example of variables 1, correlation between variables 1 and 2, it would be R subscript 1, 2. If it was variables 3 and 4, it would be R subscript 3, 4. It is depicted by a curved line with arrows on each end. And so the lines and arrows will quickly tell you whether you have a P line or an R line. And that's something you'll want to keep clear as you think through that. So our example is R subscript 1, 2, and this is the path of the bivariate correlation between exogenous variables 1 and 2. other variable nomenclature, Z is either an exogenous variable or an endogenous variable. And so you have to make sure where the Z variable appears, whether it's at the beginning of a line or if it's endogenous, it will be after an arrow. The E variable is the disturbance term. And this is the residual explanation not explained by the model plus measurement error. Remember, as we looked at correlations, when we looked at multiple correlation, we know that we can't completely explain all of the change in a variance. And so there's that error term. And in path analysis, this is called the disturbance term. Then our lines that we want to understand, if it's direct causation, has the line going from one variable to the next with an arrow showing the direction. If it's indirect causation, it has a path from one variable through another to the endogenous variable. And this is, make sure you keep this in mind whether you have direct causation or indirect causation, because indirect causation, you're going to have to take the sum of all of the variation in order to see what's happening through that path. To represent the model, you can state a structural equation for each endogenous variable. So we see our example on page 206 and 207. And so we see we have a variable Z3. And how do we analyze that, or how do we represent that? And so we see that it has P31Z1. So we have the Z1 variable, and it goes from, it's on Z3 subscript 1, Z1. But we also notice that Z2 has an impact on Z3. So now we have the P line of 3, 2, which is for what variable Z2 is doing. Plus we have the exogenous, or the outside disturbance term, and that's represented by E and 3 because it's directly affected by Z1. So you see how that works together, all of those different things. And as you look at the model that's shown, you can see these paths and understand how they're working. Z1 is P12, Z2 plus E1, and it's directly affected by Z2. And Z5 adds all of these together, 5.3, 5.4, and 5, because it's directly affected by Z3 and Z4. So you should be able now to look at the model and understand this nomenclature that describes how the model is coming together. When we go to assess the model of fit, that's really what we want to do. We understand the terms. We can now look at the models. We can read how they're working together. But the whole purpose of path analysis is to assess the model fit. How does it work between, and it's sort of like chi-square. In chi-square, remember, we had an expected variance, or expected number of people in each block, and an observed number in each block. Well, that's sort of what path analysis is doing, because it's looking at what is the observed correlation and what is the expected correlation. And so that helps us as we work through that. There are two correlations then that we work with in the assessment of the model of fit. The reproduced correlations, and those correlations that are logically implied by the model. The bivariate correlations that would be produced if the causal model were correctly specified. So these are the theorized correlations, the reproduced correlations. And to determine the reproduced correlations between variables in the model, you do path tracing or path decomposition. And this is where you start doing that model and you start adding numbers to that model. The correlation coefficient that is equal to the product of all coefficients in the path. And that's what we're doing in path decomposition, is summing up all the correlations that are in the path and then comparing them. To understand how to know which paths to include in the model, we have to know what a legitimate path is. No path may pass through the same variable more than once. No path may go backward on an arrow after going forward on another arrow. And no path may include more than one double-headed curved arrow. And those would be the lines that are indicated with an R. Now, to compute the reproduced correlations, for this lecture in PowerPoint, I will use RR as the symbol for the reproduced correlations. I cannot find anywhere how to make the R with a little caret over the top of it. I looked and tried all the different symbols that I could use, and then I did find an article that used RR as the reproduced correlation, so it led me to believe I wasn't the first person that had trouble with that. So anytime in my lecture here you see RR, that's going to be the same thing as the textbook's R with the caret over it. Now we want to review our example on page 211 to begin to understand what we're discussing. So the reproduced correlation between Z1 and Z3 is the reproduced collection 1, 3 is P31 plus R12 P32 times P32. Now notice when we have that correlation where we have the double arrowed line, we have to multiply that times the correlation that's impacting from variable 3 by variable 2. And we multiply the correlation that's impacting Z1 with the correlation of Z1 and Z3 to get the total effect. And remember, that's sort of like what we did when we squared the correlation in correlation contributions to get the total variance. And instead of squaring the correlation, we're multiplying the correlation of between the two variables and the correlation between the exogenous variable on the endogenous variable to get us a total impact at that point. Now, understanding the effects, D, if you see a point where it has D, then this is a causal path with only one link. It's a direct idea. I is consisting of 2 or more links where we have indirect. S is any path that has reverse causal direction that's spurious. And U is when you have more than one exogenous variable. You have unexplained correlations that may represent some degree of causal effect that is included but not analyzed. And remember, no model can capture everything that is occurring. So your textbook identifies these. You'll see this nomenclature, and you should understand how those are working according to how many spots there are in the path from the exogenous variables to the endogenous variables. And you see page 213 for that example. When all of the observed and reproduced correlations are computed for the model, you determine if any of the observed correlations are not significant. And you determine the observed correlations by doing a regression between each of the variables in your model. And if you find that you have the observed correlations are found to not be significant, then these most likely should be eliminated from the model, unless there's some reason, as the textbook states, that theoretically you should leave them in. So if you do an observed correlation where you do the regression between the two variables and it's not significant, then you should remove that part of the model and progress from there. When you determine the reproduced correlations, if any of those are significant, that is, they're saying they are differing between the observed correlation and the reproduced correlation by greater than 0.05, if they are, then you determine the missing paths and reanalyze until the best model is determined. And that's really where path analysis works. As I was explaining to someone today, I sort of think of it as sort of a Sudoku puzzle. You put together all of these theorized models, and you see, are they all within 0.05 of reproduced of the observed correlations? If they aren't, then you go back and you say, well, where are some other paths that could be working in this model? And as you see in your textbook, you then write those in with a dotted line to show the new paths in the model, and you test those until you get a best fit for your theory, and that's how you work that out. And we will work through that now as we use SPSS to do a path analysis where we're going to analyze the model fit.